2 is on Tuesday. And the topics, so remember that all of these exams are cumulative, so you want to look back at the old stuff, but everything up through linear interpolation. And on Tuesday, I just never got around to posting problems, so sorry about that. So by tomorrow morning, I will put up problems on linear interpolation. I'll, keep in mind that you're going to want to study for the test or whatever, so I'm not going to give a huge assignment or whatever, but I'll give some of these problems so you can work on them. So linear interpolation problems. By tomorrow morning. And then there are just a few topics, sort of things that are going to come up later that I want to talk about today. I'm not going to talk a ton about any of them, but just sort of to have them in your notes, and then they'll come up more later. First of all, does anyone have any homework questions or anything? I know which one you mean. No, I didn't. I'll do that. Will I? I hope so. But I did not yet. Yeah. Okay, well, I can't do it now. So anyways, yeah, I haven't done that yet. Any other questions? With the pressure? Yeah. Yeah, well, I have to look back and first make sure that I wrote it down right, because I just copied it out of the book, and then, yeah, if it's solvable, I need to tell you how. Yep.
So on the exam, when you say that it's like cumulative,
yeah,
are you gonna have actual problems from previous chapters on the test? I know some teachers say it's cumulative, but most of the questions are what we just learned.
Oh yeah, there'll be.
And then, like, the question might reference something like
right.
full conversion that you learned.
Yeah, I know what you mean. Well, yes, there are going to be problems like the old problems. So you should be, just sort of steadily like skimming back over those problems, asking yourself, do I know the steps to doing that problem? If you do, then you're probably good. If you don't, then you probably want to work through it a little bit. Now it's going to be, that's a good question. No, most of the emphasis will be on the newer stuff, but there'll be a couple of problems on old stuff. That'd be funny. I like that idea, but no, that's not how it's going to be. Yeah, right. Yeah, exactly. Any other questions about the test or anything? Yes. Yeah, all equations will always be given. No, I didn't. Sorry. Okay, so here's what we're going to talk about today. And so this stuff is not on the test. But I want to bring up this property called enthalpy. It's written as H. I want to introduce these things called specific heat. One is C sub V and one is C sub P. And so the meaning of those is the specific heat holding volume constant and the specific heat holding pressure constant. And then I'm going to talk about incompressible, modeling materials is incompressible. This is useful for liquids and solids. And then the last thing is the ideal gas model. And as part of ideal gases, I'm going to talk about polytropic processes. We've already done some problems that have used these, but and then once we're done with this, we're ready to go on to the next big topic, which is, so far we've used the first law of thermodynamics only in where our system is a fixed amount of material, and closed system, yeah. And so now we're going to go on to using the first law of thermodynamics in a case where our system is a volume and material is flowing in and or out. Okay, so the math's going to get a little more complicated, although the ideas stay the same. Control volume. Okay, so the first thing I want to introduce is enthalpy. Enthalpy is the internal energy plus pressure times the volume. And since all of those things that are part of its definition are properties, this is also a property. And there's a column in the tables we've been using for enthalpy. So, for a certain temperature and a certain pressure of gas or whatever, you can look up what the enthalpy is. So what is this thing, or where does it come from? I think the most accurate way to describe it is it's just a couple of terms that come up a lot through derivatives when you're doing calculations. We'll see that with a lot of the derivations that we'll go through in class, these terms just pop up, and so they pop up together often enough that we give it a name and give it its own column in the tables. But loosely, you can have sort of an intuitive idea of what enthalpy is by thinking of it as it's the internal energy of your system. Plus, if you think of that PV term, you can think of it as sort of like the work that's required to force your system into its surroundings. Okay, so it's the internal energy of your system plus the work required to put your system in its surroundings. I don't know. It's not, I think the truth is it's not going to be that helpful to have an intuitive idea, but I don't know. You can talk about that at dinner parties and stuff. Remembering how to define it, that's true. So the internal energy of the system plus the work required to put the system in the surroundings. In tables, it's given as an intensive property. So if it's given as lowercase h, that's the specific enthalpy. So that's the enthalpy per mass. And if it's given with an overbar, that's per mole. That's the specific enthalpy, so that's per mass. That's the one that we've used more often. Although moles are going to be more important when we talk about the ideal gas law. The units for enthalpy are energy.
Well, one quick question.
Yeah.
When you say work required to put energy, it puts systems in surroundings.
Mhm.
You mean spatially or energetically? Do you see what I'm asking?
No.
Well,
You could think of it as like this. If your system has a certain amount of volume, okay, and if you imagine that the pressure of the surroundings stays constant from before the system is in that place, okay, then it's the work that would be required to open up space to put the system in there.
okay, so that's what I meant.
Okay.
Okay.
Yep.
That makes sense.
Okay. Enthalpy is given in tables, but it doesn't have to be because all the other stuff is given in tables. So, like, for example, let's say you have 2 kilograms of liquid water at the saturation temperature at 1 bar of pressure. So what's the total enthalpy calculated from the specific internal energy, the pressure, and the specific volume? Okay, so what table would you use here to find this? So we need to use a table to come up with U, P, and V. What table would we use? We've talked about a few types. Well, it's saturated liquid water, so we'd use the saturation tables for water. And there are 2 types of tables for saturation, ones that are indexed by temperature and by pressure. We have the pressure here. So we'd want to use the, the saturated pressure table.
I'm sorry.
Yeah.
I always ask questions like a minute after you go.
Okay, yeah.
Okay, so and that's because they're coming into my mind.
Mm-hmm.
When you say H per unit mass, is it per gram, per kilogram?
Well, it always tells you in the table what. So no matter what your units are, if you're doing it per mass, it's a specific enthalpy. And the table gives you a few options for how to look it up. You might have to do the conversions or whatever. Okay, so from this table, the specific volume is 1.0432 times 10 to the minus third meters third per kilogram. The specific internal energy is 417.36 times 10 to the positive third joules per kilogram. So I'm just writing all these in SI units. And the pressure is 1 bar, so that's 1 times 10 to the 5th pascals. The specific enthalpy is the specific internal energy plus P times the specific volume. And so that's 417.36 times 10 to the third joules per kilogram. Well, all these are in SI units now. I'm going to leave the units off. plus 1 times 10 to the 5th times 1.04 E2 times 10 to the minus 3rd. That second term ends up being really small in this case. And so we come up with a value of 417.46 times 10 to the 3rd joules. And then if you look over at the column for enthalpy, that's what it says there. That's the specific enthalpy. To get true enthalpy that you'd use in like a energy equation, you just have to multiply by the mass. So what did I say, 2 kilograms? So 2 times H, and we get 834.93 times 10 to the 3rd joules. This 2 is kilograms. So we calculated H per kilogram. Yep, you're right. Yep. Another thing you might have to do, so what if you have a mixture of phases at the saturation temperature? So let's say we want to know what's the enthalpy for 1 kilograms of water at a pressure of 1 bar, so 1 times 10 to the 5th pascals. At saturation. And with a quality of 0.8. Okay, what does it mean that quality is 0.8? Yeah, right. So like, yeah, 20% of it is liquid, 80% is gas. So we're going to first look up the specific enthalpies for the saturated liquid, the saturated vapor, and then we're going to do like a weighted average kind of those two, or and add, well, we're going to add up the enthalpy that's in that 20% that's water to the enthalpy that's in that 80% that's vapor. So the specific enthalpy for the liquid, that's written as F for fluid, is 417.46 kilojoules per kilogram. That's the one we calculated before. The specific enthalpy for the vapor is 2,693.6 kilojoules per kilogram. It's a lot higher than for the liquid because the internal energy is a lot higher for a gas than a liquid. And then now we have to figure out the masses. So the mass of the liquid is 0.2 times the total mass. So 0.02 kilograms. The mass of the vapor is 0.8 times the total mass. So 0.08 kilograms. And so then the total enthalpy is the mass of the liquid times the specific enthalpy of the liquid plus the mass of the gas times the specific enthalpy of the gas and you get 223.84 times 10 to the third joules.
Is that always gas?
Yeah, that's always it's giving you the fraction that's gas. Yes. Always. And the way, and I mentioned when I introduced that like the way to make that make sense in your head, I think, is that if you're trying to use a substance to produce work, you often are in thermodynamics things, then you're happier. You're with the quality of your mixture. You're happier with your mixture if you have more of it vapor and less of it liquid, and that's because it's all the same temperature either way, but the vapor has a lot more energy stored up that you can use for work. I think that's a good way to sort of make sense out of it. Okay, so now, incompressible model. This will be useful sometimes. Liquids and solids. It's really never useful for gases because anything you do to a gas changes its density. But for liquids and solids, the density doesn't change very much. So you can think of this as volume and the density are treated as constant. If you make this assumption, then the internal energy of the material is approximately, the internal energy is approximately just a function of temperature. The pressure doesn't change the internal energy. And like I said up here, V, the specific volume, is assumed to be constant. So everything that you do in this model is based on these two things. Damn it, did I skip a page? Yes. I did. Test this out. Or do this. Yeah, good. Okay, we'll be back to that in a second. So first we have to talk about what specific heats are. So the rough idea of a specific heat is how much energy has to be added to a material to change its temperature some fixed amount. a given amount. For liquids, those values don't vary very much while it's in the liquid phase. So do you happen to remember like roughly how much energy it takes to raise the temperature of 1 gram of water 1 degree Celsius? What? Yeah, right, 1 calorie, right. Which is, how much is it? 4.184 joules. So yeah, good job. 1 calorie makes 1 gram of water, liquid water. Increase in temperature 1 degree Celsius. That's the idea. Yeah. Yes, it is. To change the temperature a given amount. Yep. But overall, these are not constant. And especially with gases, you can never really assume that they stay constant. And so there's a partial derivative definition of each of these two things. And depending on what values you assume are constant or whatever, you can simplify these sort of ugly definitions. But so the first one, C sub V, that's the constant volume specific heat. The definition of that is the partial derivative of U with respect to temperature evaluated at a fixed volume. That's what the sub V means. And the specific heat for constant pressure is the partial derivative of the specific enthalpy with respect to temperature evaluated at a fixed pressure.
Is specific heat sort of analogous to mass, but for what mass is to macroscopic kinetic energy, specific heat is to thermal energy?
Ooh, I don't know about that. I'll have to think about that.
Well, because mass is a measure of how much force it takes to change the
Yeah.
velocity of
Right.
the object a given amount.
Yeah, I could sort of see that. So these are the definitions. And we're going to talk about how you can use these now that I'm going to bring up that incompressible model. And later I'm going to bring up the ideal gas model. And we're going to talk about how those simplify when you make those simplifying assumptions. By the way, these will appear in quizzes, so remember those. It's because they're going to come up a lot. Okay, so now let's talk about the incompressible model. As you might guess, based on stuff you've heard about the incompressible model in the past, this is most applicable to liquids and solids. And if you're talking about an incompressible material, that means the density is constant. So like a certain volume of seawater at the bottom of the ocean has about the same mass as the same volume of seawater at the surface. Pressures are very different, but the densities are the same. So density is constant. Well, roughly constant. We're going to assume it's constant. And we're going to assume that specific volume or any kind of volume is about constant. We're not going to worry about how those vary. And with these assumptions, we get that the internal energy is only a function of temperature. And the specific volume is about constant. And everything is going to be based on these. And we're going to think about what these mean for those specific heats. So based on these assumptions, the meaning of the specific heats change, and they change in a way that are going to let us calculate things from the specific heats. So for an incompressible material, remember that the constant volume specific heat is the partial of U with respect to temperature for a fixed volume. Well, what this is saying is that in general, the specific internal energy is a function of temperature and volume. But now with our assumptions, volume isn't a variable anymore, it's a constant. And so we can think of this as a total derivative of the internal energy with respect to temperature. And if you think of the constant pressure specific heat, that's the partial of enthalpy with respect to temperature at a fixed pressure. This is based on the assumption that, thinking that, exactly the same way, that specific enthalpy is a function of temperature and pressure. And oh no, okay, so do it like this. So that's partial with respect to temperature of, think of the definition of enthalpy. So this is internal energy plus PV for a fixed pressure. And so you get that this is the total derivative of U with respect to temperature, because would you actually get, so actually in this case, let me think about this for a second. What you would get here is, so you get partial of U with respect to temperature plus partial of pressure with respect to temperature times V plus pressure times partial of V with respect to temperature. This is a total derivative. This goes away, but this we still don't know about. So pressure is not changing because we're evaluating that at a fixed pressure. That's right. Yep, you're right. Okay, so this goes away too. Okay, and so what you get is that both of these for an incompressible material end up being the same thing. And so for liquids, you don't tend to talk about two different specific heats. You tend to talk about just a single one, C. That's just the specific heat. And so now that you have this written as a total derivative, so now you have that this specific heat is just equal to du d temperature. Now you can use that to find the changes in temperature that correspond to a change in internal energy or vice versa. So here's the kind of thing you can do with that. So let's say that we want to find the change in total internal energy and the change in enthalpy for 2 kilograms of liquid water it goes from 320 Kelvin to 324 Kelvin. There is a table where you can look these up. So look up the specific heat in a table, and I'll give you that. And what you see is at 320 degrees Kelvin, the specific heat is 4.179 kilojoules per kilogram Kelvin. At 350 Kelvin, this is like, I don't have it written down, but it's like 4.181. You know, the difference is really small compared to the way the other things are changing. And so we're just going to treat this like over this entire range. You know, this is a tiny difference. So since our temperature isn't changing anywhere near 30 Kelvin, we'll assume that C is equal to 4.179 kilojoules over kilograms Kelvin over the whole range. Well, I'm just saying, so to get a different, for this to change all the way from 4.179 to 4.181, you have to go 30 Kelvin, you know. Ours is much smaller than that, and even if it was 30 degrees, you know, that's a pretty small difference. But at that point, maybe you take the average between those two. But anyways, you can see that it's not going to, you know, we could do this calculation assuming 320, do it assuming 350, doing any combination of those, and our answers would be the same.
So if it was a wider range?
Yeah, if it's a really big range, then you need to take that into account. Yeah. Okay, so we know that du d temperature is equal to 4.179. And So if you multiply both sides by d temperature, you get this, and you can integrate both sides. Who knows what that differential equation approach? Separation of variables. Yep. So integrate both sides. And so this is from instant 1 to instant 2. This is from a temperature of 320 Kelvin to 324. And so the change in specific internal energy is equal to 4.179 times 324 minus 320. And so you get 16.716 kilojoules per kilogram. We didn't want the specific internal energy, we wanted the total change in internal energy. So we have to multiply 2 kilograms times that answer, and you get 33.432 kilojoules. So now for the enthalpy, we want to calculate the change in H. Change in specific enthalpy is the change in internal energy, specific internal energy, plus P times the change in the specific volume. No, the specific volume, I did that back. The specific volume we're assuming is constant, times the change in pressure. So let's first think, what if the pressure stays constant? Then the change in pressure is 0, and the change in specific enthalpy is the same thing as the change in specific internal energy. So the change in total enthalpy is the same as it was for the change in internal energy, 33.432 kilojoules. Now, what if the pressure isn't constant? What if, as that temperature changes, the pressure goes from 101 kilopascals, normal sea level atmospheric pressure, to 140,000 pascals. Then the change in enthalpy is equal to the change in specific internal energy plus V times the change in pressure. The volume, so the specific volume is the volume of this liquid water per kilogram, and that's just, we're going to make that is equal to 1.00 cubic meters per kilogram. That's not right. 1, 2, 3. So that should be, so in 1 cubic meter, it should take, so this should be times 10 to the minus third. A cubic meter of water, of liquid water, has a mass of 1,000 kilograms. So we have 16.72 plus 1 times 10 to the minus third times the change in pressure, which is 140,000 minus 101,000. And so you get 16.72 plus 39. So 55.72. This is in kilojoules per kilogram. And so now multiply that by 2 and you get change in total enthalpy. So 2 kilograms times this. So 111.44 kilojoules. Any questions about that? All right, so I said one thing that's going to come up on quizzes is the definition of the definitions of those specific heats. I'd also like you to, also going to be on quizzes at some point, are these definitions of what the incompressible model means? Because all of these derivations come from those definitions. And now there's another model that we want to deal with. That's the ideal gas model. I'm sorry? These sort of definitions of the incompressible material model. And just like there are these two things that define the incompressible material model, there's going to be 3 things that define the ideal gas model. And I want you to remember what all those things are. Okay, because all of the derivations I'm doing in all these sections just come straight from those requirements, okay? So for ideal gases, there's this amazing fact. For any gas, if the pressure is low enough, meaning ratio of gas's pressure over the critical pressure. Remember what the critical pressure is? Anybody remember what the critical pressure is? The critical pressure is on that surface, that PVT surface. You had that main feature that was the vapor dome. And over here is where you're crossing from liquid to mix, and over here is from the mixture to vapor. And if you get above a critical temperature and a critical pressure, there's no more distinction between liquid and vapor. All there is this supercritical fluid, it's called. Gas and liquid are the same thing. So that's the pressure at the top of that vapor dome. And for any gas where the pressure is low enough and or the temperature is close, gets close to the critical temperature, if you take the limit of this, P, times the molar specific volume of the gas divided by the temperature, and you take the limit as the pressure of the gas goes to 0. Okay, so how would you do this experimentally? So think about just one gas. The pressure you don't want to be close to the critical pressure. The temperature you do want to be. Okay, the pressure you want to be as small as possible for this to hold. And so, so whatever gas, let's say air. Start with air. So you do something to it, measure the pressure, measure the specific volume, measure the temperature, and plot that on a graph with this on the vertical axis and pressure on the horizontal axis. Okay? And now you reduce the pressure, give it a little more room, take that measurement, plot it out. What you get is a smooth function, pretty linear, and without, you wouldn't have to go all the way to pressure equals 0. You just see that in the limit, this function is approaching a certain value when pressure is equal to 0. Okay, so you did that with air, and you came up with this limit as the pressure goes to 0. And now you're doing it with hydrogen gas or something. And what you would see as you did all these gases is they all approach the same value. Okay, that's a big thing. So this value is R bar. That's the universal gas constant on a molar basis. But like if you think of the way like liquids expand as you put energy into them, they don't expand very much. That's why we made that incompressible assumption, but they expand as you put energy into them. And you can quantify how much they expand. But for a liquid, you quantify it for each individual substance. You do these experiments and you get different answers for how that liquid's specific volume changes as the temperature changes. The difference here is that this holds for every gas. What we really have here is, so the ideal gas model is based on the idea that as the gas molecules spread out, yeah. Yeah, so we're going to see that, so we're going to do calculations with this R on a mass basis, but it's not universal if you do it on a mass basis, because this is true if you have the same number of molecules, but the different gases, molecules weigh different amounts. Okay, so that's why we're doing it there, because this is the one that's universal. So as the gas molecules spread out, the only significant forces come from collisions. They're far enough apart that the attractive forces between the molecules are not a significant determinant of how the gas behaves, you know. So if you think of gases as like people in sumo wrestling suits, you know, like if so if you're in a liquid or a gas with a very high pressure or a gas with a very low temperature, every pair of guys in sumo suits can pull on each other, you know. But if you spread them way out and launch them around at high speeds, they bump into each other, and there's not much you know, bump into someone like that, you can't grab them or whatever. And so that's what's going on here. You're going from having the pushing and pulling of the molecules on each other being significant to only superballs bouncing off of each other. Okay, so the ideal gas model is based on these three equations, and these are the ones I want you to remember. PV equals RT, and I'll tell you what this R means in a second, because this is based on mass. The internal energy only varies with temperature again. And the specific enthalpy is equal to specific internal energy plus R times the temperature. Okay, these are quizzy. So temperature in these two equations where it appears explicitly, temperature has to be in Rankine or Kelvin scales. It has to be an absolute scale. And that capital R without the bar is equal to R bar divided by M. Where R bar, the universal gas constant, is 8.14 kilojoules per kilomole times Kelvin. And that capital M is the mass per mole of the gas. Okay, so well, to make it work with this, it has to be in whatever units of mass you're using for pressure, I guess. You know, pressure is force divided by area. So kilogram, you know, so those have to match. And if you're going to use it with this, then this should be kilomoles. So that those cancel. So, like, hydrogen gas is H2. Every gram of, or every mole of hydrogen gas has a mass of 2 grams. Oxygen has that forms O2 molecules, and so the mass of each oxygen atom is 8. So 1 mole of oxygen gas is 16 grams. Okay, so even though there's the same number of hydrogen molecules in a mole as there are in oxygen molecules in a mole of oxygen molecules weighs 8 times as much, has 8 times as much mass. And so because of this, that capital R, that per mass gas constant, varies as you go from material to material. So this one is not universal. Any questions about this? Any of this? We're going to be using it, yeah, I guess that's the form of the ideal gas law that we're going to use. So let's do an example. Well, let's say we have 0.5 kilograms of air. In a fixed tank. And energy is added through heat. And so the gas goes from a starting temperature of 20 degrees Celsius and a starting pressure of 101,000 pascals, atmospheric pressure, to new pressure of twice atmospheric pressure, 202,000 pascals. So first, let's sketch this process on a pressure versus volume diagram. And then second, what's the temperature at state 2? And we're going to assume that this is behaving like an ideal gas. Okay, so a pressure volume diagram looks like this. That's what the projection of the vapor dome looks like. This is the critical pressure. On this side of the critical pressure, what do we know about the material on that curve? That is a saturated liquid, that's right. And what do we know about all of the states on this side? This is This is all liquid before it gets that saturation. Okay, so this is liquid. Inside the vapor dome, what is it? What? Mix, yep. And then on the other side is vapor. Mm-hmm. Not there's not a real difference. You can use them interchangeably, but people use vapor when they're talking about something that is a liquid or a solid at room temperature. So the example I gave before was steam is a vapor because at room temperature water is a liquid, but oxygen is a gas because it's a gas at room temperature. Okay. Okay, so where are we on this? We're talking about air at 20 degrees Celsius and atmospheric pressure. So we're starting over here somewhere. And then what does this process look like? It's in a fixed tank that we're adding this energy. So what does that tell us? Volume's constant, so it has to look like this. It's a vertical line. So state 1 is here, and it goes to a higher pressure at state 2. And now for part B, we're trying to figure out the temperature at state 2. We know that the volumes are the same. Let's call that V. And we know that pressure 1 times that volume is equal to R times the temperature at that initial state. And we know that at state 2, P2 times that volume is equal to R times the temperature that we want. So what we're going to do is figure out what R is for air. Our bar is 8.314 kilojoules per kilomole times Kelvin. Air has a mass of so 1 kilomole of air, you can just look this up online, has a mass of 29 kilograms. That's because 1 mole of air has a mass of 29 grams. So R is equal to 8.314 10 to the third. Now that's in joules over a kilomole times Kelvin. And we'll divide that by 29 kilograms per kilomole. So 29 kilograms kilomole in the numerator. And we get R for air is equal to 286.69 joules per kilogram Kelvin. And so now we can figure out what V is. So I'll use this one. P1 times V is equal to 286.69 times the temperature. I gave the temperature in Celsius, but for the ideal gas law, you have to do it in Kelvin or Rankine. So this is 293.15. That initial pressure is and so you can calculate that volume is 0.832 meters cubed per kilogram. And now you can put that in for state 2. The pressure at state 2 is 202,000 pascals. The volume's the same, it's fixed. Is equal to 286.69 times T2. And so T2 is 586.22. Any questions about that? R bar is a constant, and that's the one that's the same for all gases. R is a constant for each individual gas that you have to get from that universal gas constant by dividing by the mass per mole. Okay, so I'll get those linear interpolation problems up by tomorrow morning, and then there's a test on Tuesday. What? And problem 4. I'll figure that out too. And a bunch of other stuff. Yeah, Fred's homework. Yep. I'll start working out regularly, eating right.